Hello, I'm Sergio Emilio Cruz, and this is the presentation for our challenge of amplification of amino acetates. So, for starters, let's bring some context. This reaction is a primary reaction of amplification. It's base catalysis hydrolysis of amyl acetate, which contains an ester with NaOH to produce sodium amylate and alcohol. Our kinetic hypothesis is that it will be a second order, and our key objectives aiming in this investigation is to determine the reaction order and rate constant, aka K, and evaluating the steering, different steerings, 300, 350, and design a batch reactor for COMX adiabatic. The experiment, how was it conducted? Well, basically we can divide it in 5 steps. The first one is to run at different steering conditions, 300, 350. Then mixing 10 milliliters of NaOH with 10 milliliters of amyl acetate, 10%. Then we made time samples at 10, 20, 30, 50, 40, and 50 minutes of interval. We quantified the NaOH by titration with 0.67 HCl, and we use integral method to verify the second order of kinetics. These are the consecutive equations that we use. So basically, these determine the chemical behavior and physical behavior of the system. With these equations, we could determine the concentrations, equivalences, and the determination of how much concentration of NaOH was used for the system. Again, mentioning the two phases that we had on the reaction. The kinetic model and rate law that it was established is the following. R equals K times Ca times Cv. For equimolar feed, Ca equals Cv, so R equals K times Ca squared. And we use integral method to verify that it was a second order. You can see on both runs that the R fits well the model, and here we have the values of the K's that are the slope. The species and energy balances. As we are talking about a mole balance batch, this is the following formula and by definition of design of a batch reactor. We can further simplify it more as saying that again, Ca equals Cv. So this is the following equation for mole balance in a batch. Again, energy balance, we say that it's adiabatically, so Q equals 0, meaning that the heat made by the reaction will stay inside the reaction, rising the temperature of the reactor, of the reactants, and there won't be external heat exchange with the surroundings. Here is the energy balance used and all definitions implemented. Literature equations, well, we use Arrhenius equation to put K as a function of temperature. We use the rate laws integral method to determine the order and the design equation of a batch reactor and the energy balance for a batch reactor adiabatically. The results in the laboratory, we determine through 2 Ks. This one that you can see here for the 300 RPMs, and this one that can be seen here for 350 RPMs. These are the units. This is a synthesis of our case. Experimental values were 100 times lower due to mass transfer limitations in the lab. The heat of reaction that we use and we find on literature was minus 60,000 kilojoule kilomole, and the activation energy can be seen also here below. We use Polymath for the design as for a software to design the reactor because we have 2 differential equations. So aiming to produce 1 ton kilograms of soap, we use a volume of 38,000 liters equal to 38 meters square, cubic meters. For a conversion of 90%, we need 15 hours of species in the reactor. Here you can see that the plots, time versus concentration, and time versus conversion, and time versus concentration. We only see 2 lines because again, Ca equals Cv, Cc equals Cd, and the equimolar and stoichiometry of 1. Well, our results, basically, we reach a 90% of conversion, but in 50 hours, showing a second order behavior. We have mass transfer limitations. Experimental K was 100 times lower than literature K. We think that it's about the physical mixing, nor intrinsically the chemical speed, and the volume was low in the lab. The mixing paradox, well, counterintuitive, K decreased at 350 RPMs versus 300. So a higher agitation likely causing inefficient mixing or vortexing, reducing interfacial contacts. Also, our main takeaway is that the system is mass transfer limited, not kinetically. The primary bottleneck is a physical contact between the immeasurable phases. In our conclusions, the amyl acetate amplification is a second order kinetics confirmed. For a production of 1 ton, 90% of conversion, or in a 38 cubic meters volume, we need 50 hours of reaction, of time, sorry. And the require optimal mixing and price temperature control is required for efficient operations. And for a future scale up, we enhance interfacial area and mass transfer efficiency to determine more efficiency in the reaction. And now this is I love this photo on our final exam of reactors. Thanks a lot, professors, for being our tutors in these courses. We learned a lot, and we will never forget you. So see you on the next semester. Have a nice day, a nice night. Good night.